Okay, so chapter 5, we're going to be talking about z-scores, the location of scores in standardized distributions. So just to recap from last week, we've talked so far about parameter and statistic. So a parameter is to population as a statistic is to sample. A parameter is a measure of a population and is denoted with Greek letters. A statistic is a measure of a sample and is denoted with the Latin script, Latin letters. We talked about nominal, ordinal, interval, and ratio, scales of measurement, and we talked about discrete and continuous variables. We've calculated some descriptive statistics and done some data visualization, which is the shape of our distribution. We've looked at measures of central tendency and variation, and now we're moving toward inferential statistics. So what is a z-score? A z-score is also called a standard score, and it gives you an idea of how far away from the mean a data point is. Technically, it's a measure of how many standard deviations of below or above the population mean a raw score is. In a standard normal distribution, which is normally shaped, it has a mean of 0 and a standard deviation of 1. So in a standard normal distribution, the sign of the z-score, plus or minus, signifies whether the score is above the mean over to the right or below the mean over to the left. The numerical value of the z-score specifies the distance from the mean by counting the number of standard deviations between the score and the population mean, so x and mu. So why do we use these? The purpose of z-scores or standard scores is to identify and describe the exact location of each score in a distribution. So suppose you received a score of 76 on a statistics exam. How did you do? Your score of 76 could be one of the best scores, or it could be one of the lowest scores. To find the location of your score, you have to transform it. You have to have other information about the other scores in the distribution, and we could transform it to a z-score. So if we look and we see that in the first distribution, the mean is 70 with a standard deviation of 3, and you scored a 76. You're 2 standard deviations above the mean, so you did fairly well. If in the second distribution, the mean is 70, but the standard deviation is 12, you're within 1 standard deviation. You're halfway through, so you did better than most people, but you are within 1 standard deviation of the mean. And if you remember, 68% of the people will fall within 1 standard deviation plus or minus, so this is considered an average score. So the z-score formula, and I'm showing it to you because you'll see it again, you'll see it as a t-score, but we're not going to do much hand calculation. I'm going to show you how this is done, and then we're going to let the computer do it for us. But a z-score definition is adequate for transforming back and forth from x values to z-scores, as long as the arithmetic is easy to do in your head. This is just a boilerplate slide, but what we have here is we have the z-score is the score minus the population mean over the standard deviation. And if you remember, these are parameters, obviously because they're Greek, and we don't usually know these. So we teach z-scores as an introduction to t-scores, and right now we're just speaking hypothetically because we typically don't know the population mean or standard deviation. But that being said, another purpose for z-scores is to standardize an entire distribution. So a common example of standardized distributions is the distribution of IQ scores. Although there are several different tests for measuring IQ, the tests usually are standardized so that they have a mean of 100 and a standard deviation of 15. So if we look at the Wechsler intelligence score, you see that the mean is 100, and here we are at 68% of the population will fall between plus or minus 15, so between 85 and 115 is considered average intelligence. And then 1 standard deviation above that, so you're now 2 standard deviations above the mean. We've now captured, going both ways, 95% of the population. So 95% of the population will fall with between 2 standard deviations from the mean. And then over here, if we look between 2 and 3 standard deviations and between 2 and 3 standard deviations below, only 2% of the population here and 2% of the population here will fall between plus or minus 3 standard deviations. So all told, everything together will approximately be about 99.7% of the population. So other relationships between z, the score, the population mean, and the population standard deviation. In most cases, we simply transform scores, which are x-values, into z-scores, or change z-scores back into x-values. But you have to realize that a z-score establishes a relationship between the score, the mean, and the standard deviation. And this relationship can be used to answer a variety of different questions about scores and the distributions in which they are located. So let's just look briefly. Let's just look at the picture first. Here we have a normal distribution with a mean of 65 and a standard deviation of what? All right, it's showing us that between 65 and 59, that's 6 points, but we've got 2 standard deviations here. Okay, so half of 6 is 3. If we calculate it out, they've told us that we have a mu of 65, which goes here. We have a mean of 59, which goes here. If we look at our calculation here, we have score minus mu over standard deviation. So the score is 59 minus the mu over the standard deviation, which is not given to us. We're supposed to calculate for sigma. We know that z is -2. All right, if I multiply both sides by sigma, I get -2 sigma over 50, or equals to 59 minus 65, divide both sides by 2, calculate this out, and I get 3. I can tell just by looking at this that half of 6 is 3, but I wanted to show you the calculation. All right, let's just look at this one visually. Okay, let's look at the normal curve we have here. We have 2 scores, 42 and 54, and we see that 42 corresponds to a -1 standard deviation, or -1 z-score rather. We have 0 as the mean, +1, and then +2 corresponds to our 54. We see that the distance between these 2 points is 12 points, and we've divided these into 3 segments. So we know that this standard deviation has got to be 4. So 12 divided by 3 is equal to 4. So we need to know, in order to know what the mu is, what that mean of this particular distribution would be, it would be 42 plus that 4, which would be 46. That's just how the z-scores work. I'm building toward inferential statistics here. Okay, so using z-scores to standardize the distribution, it's possible to transform every x value in a distribution to a corresponding z-score. If every x value is transformed into a z-score, then the distribution of z-scores will have the following properties. Okay, these are in red because they're important. The distribution of z-scores will have exactly the same shape as the original distribution of scores. Just because you transform them to a standardized distribution does not change its shape. The z-score distribution will always have a mean of 0, and the distribution of z-scores will always have a standard deviation of 1. So let's look. A z-score transformation. Here we have a mu of 100 with a standard deviation of 10. We transform our x values to z values, and we get a mu of 0, standard deviation of 1. Using z-scores to standardize, a standardized distribution is composed of scores that have been transformed to make predetermined values for mu and sigma. Standardized distributions are used to make dissimilar distributions comparable. So you can see up here we have mu of 3 with a standard deviation of what appears to be 2. And here we have a mu of 0 with a standard deviation of 1. The shape of this distribution has not changed at all. One advantage of standardizing distributions is that it makes it possible to compare different scores or different individuals even though they come from completely different distributions. Normally, if 2 scores come from different distributions, it's impossible to make any direct comparisons between them. Using z-scores makes these comparisons possible. Alright, so if all the scores in a sample are transformed into z-scores, the result is a sample of z-scores. Transformed distribution of z-scores will have the same properties that exist when a population of x values is transformed into z-scores. The sample, I've already said this, will have the same shape, it will have a mean of 0, and we'll have a standard deviation of 1. Now we're looking at the Latin, right? We're now talking about samples as opposed to population. That's the only difference. Okay, let's move into probability. The role of probability in inferential statistics is that it is used to predict the type of samples that are likely to be obtained from a population. It establishes a connection between our samples and our populations. And why do we need this? Well, like I've said many times, if we knew these measures of our population, we wouldn't need to take samples. We would just go get it from the population. But we don't. It's too costly. The population is too large. And we use our samples to be representative of the population, and we just do our data collection from a smaller sample to represent the entire population. So inferential statistics relies on this connection when they use sample data as the basis for making conclusions about populations. For a situation in which several different outcomes are possible, the probability for any specific outcome is defined as a fraction or proportion of all the possible outcomes. So if the all possible outcomes are identified as A, B, C, and D, and the probability of A is the number of outcomes classified as A over the total number of possible outcomes. Let me see if I have that. So let me make that a little bit clearer. If I have a 6-sided die and I want to know what's the probability of scoring a 1 or throwing a 1, it's 1 is the only number of outcomes classified as possible, is just 1 out of 6. So it'd be 1/6. For the definition of probability used here to be accurate, it is necessary that the outcomes be obtained by a process called random sampling. So we want to randomly sample from our population in order to have the most possible outcome of it being representative of the population. So a random sample requires that each individual in the population has an equal chance of being selected. A sample obtained by this process is called a simple random sample. An independent random sample requires that each individual has an equal chance of being selected and that the probability of being selected stays constant from one selection to the next if more than one individual is selected. What does that mean? That means that each time somebody is selected, you put them back into the pot so that the same probability of being selected the next time remains constant. It's called sampling with replacement or sampling without replacement. Typically when we're doing research studies with large samples, we don't worry about it because the differences are negligible when the samples are really large, like 1,000 people, 2,000 people. But when you're getting down to really small samples, it can have an effect. But for our particular studies, we're not doing simple random samples at all, so it doesn't really matter, but I just want you to know what the difference is. So why does sampling help? It's impossible to test everyone on everything, so there's too many people, too many items, and it's too expensive to do everybody in the population, so we use samples to approximate or generalize back to our population. Okay, so I've showed this to you before. You've seen this square where you can see that we have a fairly large sample, but even though we have a random sample, we can't really tell what the picture's showing us. If we sample more than that, double our sample, you can start to see what's behind the gray here. And if our sample is big enough, we can make out that that's the picture of Einstein. But if we sample, this is sampling individuals, if we sample clusters, you can see that we don't get a clear picture. Or if we have exclusions from the population, such as maybe people who are 65 or older, we don't have anyone 18 or younger, or we only have females, we miss chunks of the picture that we cannot get back. So we have to, the best way to sample is to do simple random samples, but in education studies we typically don't have that ability because students come to us already assigned in classes. Okay, so the normal distribution is symmetrical with the highest frequency in the middle and frequencies tapering off as you move toward either extreme. Because the locations in the distribution are identified by z-scores, the percentages shown in the figure apply to any normal distribution regardless of the values for the mean and the standard deviation. So let's look at the normal curve. All right, we've seen this a bunch of times. We know that the mean is 0, standard deviation of plus or minus 1, we get 68%. Plus or minus 2, we get 95%. Plus or minus 3, we get about 99.9%, 99.7%. So if my z-score is here, right, would you say that this is the body and this is the tail? Or would you say that this is the body and this is the tail of this particular distribution? Well, we'd say that this is the body because it's the bigger hump, and this is the tail. Well, now the z-score is here. We're just on the right side of the mean. So which one's the body and which one's the tail? This is the body and this is the tail. Okay, so we can use the unit normal table, which lists several different proportions corresponding to each score, z-score in the location, or each z-score location rather. Column A of the table lists the z-score values, and for each z-score location we have B, C, columns B and C list the proportions in the body and the tail respectively. Finally, column D lists the proportions between the mean and the z-score location. Because probability is equivalent to proportion, the table values can also be used to determine probabilities. Let me say that again. Probability and proportion are equivalent. So you can find the probability by finding the proportion underneath the z-score table. I'm going to show you how to do this in just a second. So I know you don't have the textbook, but I have in the Blackboard site the whole unit normal table scanned in. And what I was describing in this slide is what I'm talking about here. So in column A we have the z-score. In column B we have the proportion in the body. In column C we have the proportion in the tail. And in the column D we have the proportion between the mean and the z-score. Okay, and it's only positive, but we can use, if it's a negative, we can just use the same thing because it's symmetrical. The proportions will be the same going this way as it will be going this way. So, what proportion of the normal distribution corresponds to z-score values greater than z is equal to 1? First, you need to sketch out your normal distribution, right? So we put our z-score at 1, and we want to know greater than. So when we do that, greater than points to the right, so we're going to be looking to the right. And I'll show you examples that make this very, very clear. So we're looking at the proportion in the tail, okay? Let's do it for each one of these and I'll be very clear about what I mean. Okay, so if I want to know what is the proportion of a z-score less than 0.25, okay, so I'm going to score it. It's positive, right? It's about, this looks, I didn't do it quite right, it looks like more of a third, but it's between 0 and 1 is 0.25. It should be about a quarter of the way there. We know that because we're on this side of the hump, that this is the tail and this is the body. Because this arrow is pointing to the left, we're looking for the proportion in the body. We're looking for this chunk. So I come down, and it happens to be in the first row of our unit normal table. I find 0.25 and I find proportion in body. I go over here and I write that down, 0.5987, move the decimal places over 2 times or multiply by 100 and I get 59.87% of the probability or the proportion is in the body. That's how I find it. What if I want to know z less than negative 1.25? Well, the negative tells me it's to the left of the mean, so I put it here, and I want to know going this way to the left, so I'm looking for the proportion in the tail. Now, it was body this time, but now it's the tail because this is the smaller chunk. So I go and I find 1.25 because I'm not going to find a negative in the chart. I'm not going to find a negative in the unit normal table because they're symmetric, they only give us the positives. And I see that I want the proportion in the tail, so I go 1.25, I slide across the column C for proportion in tail, I get 0.1056 and I write it down, multiply by 100, and I see that 10% of the probability is to the left of the tail. Let's do z is greater than 0.80. So I put my 0.80, it's between 0 and 1, I put it here, and I now know that I'm looking for the proportion to the right, which is now the tail. I go find 0.80, sorry this was underlined in my copy, but you can see it. I get 0.2119, or 21.19% of the probability is to the right. Let's do one more. Now I'm at z is greater than negative 0.75. So that's to the left of the mean. So I'm here, I'm at negative 0.75. I'm still looking to the right because it's greater than, I'm going this way. And I see that 0.75, the proportion in the body, is 0.7734 or 73, I messed that up, 0.77.34%. I need to fix that. And so you see how that works. So why do we care? Who cares? We, again, know that 68% is here, 95% is here, and what we're looking for is eventually, we want to know what's happening in the tails, okay? We're never going to have to do this. I used to make people actually do this by hand. We're not going to do that. I just want you to see where we're going with this. If we find a test statistic that lands within 2 standard deviations, plus or minus, roughly, it's common. It's normal, right? That's average, or slightly above average, slightly below average. But if I find a test statistic way out here or way out here, that's impressive. Just remember that. That's where we're headed. So we consider we have a population that's normally distributed. We have a mean of 400 and a standard deviation of 20. We take a sample, okay? So a sample of this, say this is all high school teachers in a particular district. That's our population. We take a sample of whatever size. We implement a treatment, and then we test our treated sample. We want to know if the treatment has had an effect. So the researcher simply compares the treated sample with the original population. If the individuals in the sample have scores around 400, the original population mean, then we must conclude that the treatment appears to have no effect. On the other hand, if the treated individuals have scores that are noticeably different from 400, then the researcher has evidence that the treatment does have an effect. The problem for the researcher is determining exactly what is meant by noticeably different from 400. Probability helps researchers define noticeably different, which we will eventually call significantly different. So like I say, a hint, when we find a test statistic way out here or way out here, it's noticeably different. Okay.